All right, so now I'd like to introduce you to someone who's been really instrumental in GrafanaCloud, the third co-founder of Grafana Labs that you guys haven't met yet, our CTO from Australia. He's crazy, he's a crazy Australian, and he's from a place where everything that's alive wants to kill you. So, you know, I go visit him probably a couple times a year, and I'm grateful every time I make it out alive. But please give a warm hand for our CTO, Anthony Woods.
Oh, hang on, Raj. I need your clicker, Raj. Raj? Thank you. All right, thank you. Yes, my name's Anthony, co-founder and CTO. So I'm going to talk to you a little bit about our GrafanaCloud platform, a little bit about how we scale it, how we operate it, so that we can deliver a great experience for our users. So when we were building the platform, we had some key ideas of what we wanted, kind of features that we wanted to be able to have. We wanted it to be scalable for our customers, but also scalable, for our SRE teams. We wanted fault tolerance and automated recovery. There's lots of moving parts, so we knew service discovery was an important component. We obviously wanted horizontal scaling because we knew it was going to be popular and we're going to have to grow really, really fast. We wanted resource management and isolation. So, what did we want? We wanted Kubernetes. It's no secret, lots of people are using it. It's become super popular recently. For us, it's been worked out really, really well. We started using it in late 2015. I think it was Kubernetes 1.3 at the time. For us, it gives us a really consistent platform for deploying our SaaS solution in the cloud, but also we use it for our shippable SaaS version for on-premise deployments as well. So whether customers already have a Kubernetes cluster, we can help them spin it up for them on their existing hardware. And obviously, now there's fully managed Kubernetes solutions from the likes of Google, Azure, and Amazon. The great thing is though, you're not constrained to that. If you are in your own data center and you are running on bare metal, you can still use Kubernetes and provide that great abstraction layer. We used to run our own Kubernetes clusters. We now are transitioning to using GKE. Just reduces the operational overhead. We saw Kubernetes was great, but it was a growing project, always changing. It was almost a full-time job for someone just to keep upgrading all of our clusters. So by the time we'd done some testing and planning and get a cluster upgraded, a new release was around. So moving to a hosted platform and a managed platform is great. The pricing is great because most of them they don't have additional fees anymore for running your masters. You just pay for the compute. So that's working out quite well for us. So there's two core components within our Grafana Cloud, and that's our hosted Grafana and our hosted metrics. So for hosted Grafana, we really wanted to provide dedicated Grafana instances for every customer. The main driver for that is we wanted everyone to have the full Grafana experience. We wanted them to be able to install plugins that were appropriate for them. We wanted them to be able to configure Grafana exactly how they wanted it, whether it's custom authentication, or they've got some kind of special requirement for what they need. If Grafana supports it, we want our customers to be able to do it. We also wanted to have one-click installation from Grafana.com. So as you're browsing the catalog of plugins, you can select the one you want, click a button, and it will get deployed to your instance straight away. And we also support the basics like custom domain and custom authentication. And who better to support it than us? So this is what the stack looks like. So we run inside a Kubernetes cluster. And the real brains of the operation is a service we call our HG API, and that just runs inside Kubernetes and opens up an API endpoint. When a customer goes to Grafana.com, they can request an instance, and that will just fire a request out to an available cluster, and the API will then take care of the rest. So it's very simple for our Grafana instances. It calls out to a MySQL cluster that's shared between all instances, creates a database, creates a user. And then it just calls out to Kubernetes to go and create a deployment and a service for that instance. Kubernetes will then handle bringing up the Grafana instance. It'll pull down the latest image of Grafana that's available, ensuring we have the most recent stable release. And then once that starts up, that instance will call out to the API again, retrieve its config, retrieve a list of plugins that it needs, make sure they're all up, and then bring the Grafana process up. Once it's running, we have it sending, obviously, Grafana has a lot of internal metrics about how it's performing, and we ship those out via a Carbon Relay NG to our own hosted metrics platform in a dedicated instance, which enables us to do monitoring of all the instances and ensure everything is working properly. For exposing the instances to the internet, we use the Nginx ingress controller. Typically, you would create an ingress resource for each site that you have, but we had significant scaling issues with that just due to the sheer number of instances we had. We just almost, the controller was just in a constant loop of rebuilding its config and reloading Nginx. So we just made a small change to the Nginx template that it uses and just added our own service rule. And so we just do like a wildcard match on the domain. Sorry, and then we just route that directly to the service. So we don't have to now add a new resource when we add a new instance, and as soon as the instance is online, it can immediately receive traffic. And we just use the default backend points to our API so that instances that don't exist or are rebooting or starting up, we can tell customers exactly what's happening and it all keeps working. Customers that want a custom domain, we still use an ingress rule for. And so that way they can have their own domain name, and then we use Let's Encrypt for an SSL cert for them. Okay, so with all the metrics that we're coming out, we obviously have some great insights into how each of the hosted Grafana instances is running. This helps us, monitor them for, performance and availability, and it also gives us some key metrics about, usage patterns and, what areas, what kind of resources do we need to ensure we have for these customers and how they're being used. So, there's lots and lots of metrics available, and this really helps us run the platform. So now onto our hosted metrics platform. This one's a little bit more complicated. When we wanted to build it, we wanted something with unlimited scale. Obviously, limits do apply. But the focus for us when building it was we really wanted to target really large metric volume. So customers that are, reaching hundreds of millions of data points per minute. We really wanted to focus on the alerting use case. You're seeing a trend for people moving their monitoring to actually alerting based on metrics. So we wanted to make sure we had exceptional query response times and able to handle very high query rates. And we wanted something that was tunable on a per customer basis. Everyone's kind of use case is different, the types of data that they're sending, the types of queries that they're making. So we wanted to have some flexibility there. And obviously we wanted something fault tolerant. And so this is our stack. It's very similar to what we do with our Grafana instances. We have a service endpoint that we run that takes care of it. It's a lot more complicated and it does a lot more. But the premise is very simple. You request an instance on grafana.com through the UI, and that calls out to the API, and then it will then kick off some jobs to go and take care of provisioning it. So we start off with creating a key space in Cassandra and creating some Kafka topics for the user. And then we go and create a number of different deployments and services inside Kubernetes. And for these specific, for hosted metrics, we just use a stock ingress controller, and we just use ingress rules for everybody. So within the platform, the Cassandra and Kafka are shared, but we obviously have isolation between customers. And so that way we can just have horizontal scaling of storage. And all of our compute resources, like our query engine, is all individual to each customer. So there's really three main core components. Our own metric tank, which is our query engine, compatible with both Graphite and PromQL. It keeps a large chunk of data in memory to serve queries. Thanks, Matt. So it keeps a large chunk of data in memory for really fast queries, which we found to be very effective. It does the compression of our data and then stores it into the backend store. So the compression is based off inspired by the Facebook Gorilla paper, very similar to what Prometheus and Influx do. And we see an effective point size of about 2 bytes per data point. The other key component is Kafka. We use that on our input queue for buffering our queue and providing some resilience as we accept data. And then we use Cassandra and now also BigTable as a backend storage for long-term data. Both Cassandra and BigTable, horizontally scalable storage. Cassandra's been really great for us. It's fairly easy to run, but as we're scaling out, the process of adding additional nodes constantly all the time is becoming a little bit of an operational overhead. So we're looking forward to using BigTable, which has a much nicer workflow for us. So within each customer, they have their own dedicated stack essentially. We have a gateway service which does authentication, and then for queries, it'll just route it through to the appropriate endpoint that's going to serve that query. For ingestion, it just writes the data to Kafka. So we use three-way replication in Kafka just to make sure we have, guarantee that we're not going to lose the data. And we only acknowledge the data once all three replicas have acknowledged that they've got the metric. So if we return an OK back to the user to say we've accepted the data, it's guaranteed that we've got it. From there, we run, to handle scaling of our customers' data, we shard the workload volume between many shards, depending on the volume of the customer, and our API service will handle upgrading and transitioning that as we needed. But within each shard, we have 2 read nodes and 1 write node. So the write node just ingests from Kafka, does our data compression, does aggregation, and then flushes it to Cassandra. And the read nodes do the data compression and aggregation, but they don't flush anything to Cassandra. They're just there to serve queries. And the main reason for splitting that out was just to make guarantees that, queries couldn't interrupt our write process. So, we're always going to be able to accept your data and store it. And it just provides a little bit of safety. And then we have 2 read nodes just for redundancy, and we can scale that out, to additional replicas if we want. So that's working out really well for us. Again, as with Hosted Grafana, we have a lot of internal metrics about how things are performing, and we ship that off to a Carbon Relay NG and then back to our operations center. But one nice thing that we also do for the hosted metrics is we aggregate some of that data and then feed it back into the customer's instance. So this gives the customer visibility into exactly how their instance is performing. So they can see key metrics on usage, so their ingestion rate and the number of cardinality and number of active series. They can see metrics on their query rate and the latency of all of their queries. We have some good points on complexity of their queries, so the number of data points needed to be fetched to render the query and the number of series that are touched for that query. And obviously we have some information on caching and how effective the cache is for them. We have exceptionally fast query response times. Our mean response time across the cluster is about 250 milliseconds, and our 90th percentile is less than 3 seconds. And really what this comes down to is caching. 99.5% of our queries are served out of memory. So we don't have to hit the back end very often, and when we do it, it's pretty quick. And this enables customers to do really high query rates and also really large queries. We have some customers that regularly, through their alerting engines, send single queries that aggregate more than 80,000 series in a single query. And I think there are some others that are doing larger. Okay, so we've been really happy with Kubernetes, from operational efficiency. It's really, helped us accelerate and build the platform. We're also really excited to start using BigTable and also see some additional operational efficiency there as well. And so on that note, I'd like to invite Misha Brookman from Google, who's going to talk a little bit about BigTable. Thanks, Misha.
Product manager for BigTable at Google, and I'm going to talk about Google and BigTable and how they relate to each other, where it comes from, and how it works in Google Cloud. So Google originally started with the mission of organizing the world's information, making it universally accessible and useful, and originally that meant building search. And search is just one of the products now that Google has built. There are a large number of other products that are all having the same concerns about management, scalability, and the data management and the processing that they need to do at scale to manage it for the number of users that they all have. So originally there was a question, how do we run and update a large number of products and services at scale? So in particular, Google started with containers, and Google contributed C group support to Linux that enables containers today. So originally, we wanted to build something that would make it really efficient and simple to make it possible to run these containerized workloads. So we built Borg, and then we open sourced a version of Borg as Kubernetes that you know. And we now provide a managed service for Kubernetes, which is Google Kubernetes Engine. Another issue for us was how do we scale to handle petabytes and petabytes of data in a database. So originally, the index that was built for web search was built using a file system, the Google file system, which has been upgraded to Colossus. However, when you're building an index on a file system, you're doing it in batch mode. And so every time you're reindexing the entire internet. You're reprocessing all the data that is growing and growing and growing. What you really need is to be able to update individual bits of web pages or individual web pages, because some of them upgrade much more frequently than others, and you want to be up to date. You don't want to have stale indexes, but at the same time, you need to be able to scale and handle the update rate that happens. So we needed to build something that would scale with the growth of the internet, so we ended up building BigTable. And today we offer BigTable as part of Google Cloud, so you can get access to the same technology that is used by a number of products at Google, starting with web search, and with a number of products today that is offered as a fully managed service as part of Google Cloud. We've published a number of papers in the past that helped us build a number of the products that we have for consumers. And the products that benefit from this all benefit from the scale that the technologies that we built have provided, starting from compute to storage to databases to analytics. We now have, the app developers can now stop thinking about how do we scale a storage system or a computing platform, and they can just think about the business aspects and the application-specific logic that they need to build, given that scale is basically a solved problem for them. And all of these products that I mentioned here have scaled very well. Each of these products now manages and supports over 1 billion users each, and there are other products at Google that support tens of millions or hundreds of millions of users. All of this is possible because they can rely on the same underlying infrastructure, both from the hardware perspective as well as the software perspective. Right? So the technologies that we've built are generic. They're applicable to a number of domains across a number of different areas, from video streaming to email to analytics to everything else. And those products are now available as part of Google Cloud Platform, from compute to databases to storage to machine learning, et cetera. I'm going to concentrate on just one of these today, which is BigTable. So BigTable, or Google Cloud BigTable, it's a fully managed NoSQL database. One interesting thing about it is that it has a built-in support for time series. And it provides seamless scalability for throughput, and it learns and adjusts to access patterns. So let's talk about each one of these items in turn. BigTable provides a single row key model. It's a NoSQL database, so it's a no-join model. It provides atomic operations across any values in a single row, and it's a sparse database, which means unwritten values don't take up any space. Here you can see how the addressing works in a BigTable table. So there's row keys, there's column families. Within a column family, there are column qualifiers, and you can address each one of those cells independently. Most databases are two-dimensional, so rows, columns, and cells. However, BigTable provides a three-dimensional model, and that third dimension is a time dimension. So every one of the cells is actually versioned. It has an int64 attached to it, and now you can treat that as an arbitrary version ID 0, 1, 2, but you can also treat it as time, and it is very frequently treated as time. This enables you to store time series natively in BigTable as a first-class citizen, and this is something that Metric Tank and other systems take advantage of to efficiently store the data in a time series format, as well as query it in a time series way. You can optionally set expiration, so you can say keep at most n values, or keep data that is only younger than 7 days. You can set a combination of those, or you can say retain everything, do not garbage collect. I will manage my own data lifetime myself. Those are all options that you have. I'm just going to go through a high-level architecture and how BigTable works internally to explain how is it that it provides the seamless scalability and how we do upgrades and how we manage BigTable at scale. So clients connect to BigTable not directly, but through a load balancing proxy layer. That is that middle bar in the middle. I'm going to remove that in the following slides for clarity of request routing, but keep in mind that clients don't need to discover or update or know where the individual server nodes are that are serving them. They get a single endpoint, and they connect to it, and we route the request accordingly. So clients connect to BigTable nodes. So BigTable as a database is actually a stateless storage system. BigTable nodes themselves store no data. BigTable, as well as other Google native storage systems, all store data in Colossus, which is our distributed file system, which is a successor to the Google file system. There is a Colossus file system in every data center. It is the size of the data center, and all the data that is in that data center is stored in Colossus. So BigTable nodes don't require to be co-located with the data because the network is fast enough for them to not have to have that as a requirement. So they can be on completely different machines in the data center and still have access to it. BigTable manages different chunks of data that is stored in Colossus. And so clients are routed to the right nodes that manage that. And because we provide atomic operations, they need to have exclusive access to pieces of the data. The keys are sorted lexicographically in any given table. They're split, and they're assigned to the different processing nodes. So if we notice that a single node is getting more activity than others, what we can do is we can seamlessly reassign the responsibility for the data to a different node without having to move any data. So we can manage terabytes or petabytes of data and reassign data very quickly without having to worry about copying the data over. This also means that we can seamlessly scale clusters in place on a running system without any cost or any downtime, because we can seamlessly reassign the responsibility for the data from one node to the next. This is also how we do upgrades. This is also how you can scale up and scale down clusters without any loss of connectivity or access or performance for the BigTable cluster. The BigTable nodes don't talk to each other. They do not communicate amongst themselves. So you get linear scalability. So whether you have 3, 30, 300, or 3,000 or more nodes, you get linear scalability in performance in terms of the number of rows you can touch per second, the scan throughput that you get from the data. And we've done a lot of optimization to get really low latency at tail. So we get single-digit milliseconds at the 99th percentile. We have a native scheduler that protects the path of user requests from the internal management, such as compactions. We don't have any garbage collection. The system is written in C++, not in Java. And we have very fast tablet reassignment. Those are the key ranges that we have, which makes it possible to have a highly managed system at scale that can grow and shrink the clusters as given. So in summary, it's a fully managed database system, built-in support for time series data. It learns and adjusts to usage patterns, and it provides seamless scalability for throughput. And with that, I'll hand it over to Dieter to talk about Metric Tank. Thank you.
Thanks. Hello, everyone. Hello, live stream. Hello, YouTube from the past. I'm Dieter. I'm going to talk about Metric Tank. If I get these buttons to work, hold on. Oh, okay. All right. So one thing to clarify, Metric Tank has come up a few times. Metric Tank itself is part of a product, it's part of GrafanaCloud, but by itself it's not a product, it's a project. So I'm making the distinction because if you want something easy to use, easy to operate, use GrafanaCloud. Metric Tank by itself, if you try to run it just itself, you're going to have a little bit of a harder time. Yeah. I'm pointing at the laptop. Closer. Okay, here we go. So where did the Metric Tank come from? A little history lesson. Back in 2015, life at Grafana Labs was pretty simple. We just had one hosted offering, which was WorldPing. And for WorldPing, we were looking for a time series database. We were not really interested in writing one ourselves, because the less work we had to do, the better. So we wanted something that was able to handle millions of points a second, something that was able to provide long-term storage, because some of our customers need that, something with rollups, ideally like Graphite, something that is resource efficient, so something that had to consume little CPU and memory. At this scale, it's important. Disk usage was very important. A lot of the solutions use too much disk space. Support for multi-tenancy, because we have a lot of different customers. They need to be able to run on the same system. Something that has to be open source, that's important to us. Something ideally operationally friendly, because we have limited manpower. Ideally proven technology. And ideally also compatible with Graphite, or at least something that we could connect to Graphite, because Graphite was really important to us. So for a while, we were trying to figure out the answer to this. It was really hard. We played with Elasticsearch for a little bit, but it wasn't really as well suited to the metrics use case. It used too much space. We played with InfluxDB, but the data model wasn't quite right for us, and then they closed sourced the clustering. We were pretty happy with KairosDB for a while, but it was also less efficient than we would like. So for a while, we were trying to figure this out, but we were definitely not interested in creating yet another time series database. So we were trying to figure it out. For a couple of months, this went on. Then I came across this paper from Facebook, the famous Gorilla paper, where they describe their system and their very interesting and efficient compression system. And that kind of started things rolling for us. There was also this open source Go library that implemented the algorithm, and this is the same library that is used in InfluxDB and in Prometheus. And so I realized, okay, the library exists for the compression. We can take a queue that already exists. We started with NSQ, we later switched to Kafka. Then we just need a storage system like Cassandra, which solves a lot of the storage problems for us. And we also started out with Elasticsearch for indexing. We later migrated away from it, but basically all these pieces were there. We just had to glue it all together into a solution. So we started prototyping this in September 2015. We actually rolled it out in production in December 2015 for our role-playing environment. But at this point, we were still asking ourselves, do we really want to write another time series database? But then 2016 came, customers were starting to pay us money so that we could give them a hosted metrics offering. We ran Metric Tank for them. We still weren't really quite sure, do we really want to pursue our own metrics database? Then GrafanaCloud V1 came, again, based on Metric Tank. I guess at that point, it started becoming more and more clear, okay, we're going to do this. Now, of course, there's GrafanaCloud version 2. We're always looking at alternatives, especially now that Prometheus is here, we're looking at ways of making Metric Tank better. But it looks like we're going to proceed with Metric Tank and invest more in it. But we're always open and looking around in the open source ecosystem, like is there a bigger project that we can be a part of rather than creating our own ecosystem? Because that's what we're trying to avoid. So Metric Tank, let's just go over briefly what it is. Well, simply, it's a service. It reads time series data from a queue. It compresses all the data into chunks, and then saves those chunks to a database. The compression is really key here, because this is what allows us to keep a lot of data in memory, and it allows us to have a much decreased workload on Cassandra. Like other databases that use Cassandra, Cassandra needs a lot more resources if you store individual points. But once you start batching up data and start saving chunks in Cassandra, all the CPU memory requirements, everything goes way down. It also saves rollups, of course, because we need them. It has an in-memory component and as well as the database in case it cannot satisfy the queries. We have several input mechanisms, but the preferred one for the clustering is through Kafka. This allows us to save Graphite data, Prometheus data, OpenTSDB data. Everything goes through Kafka, and it's also the basis of our clustering approach. You can input into Metric Tank directly with the Carbon protocol or with Prometheus writes if you want to, but that just makes the clustering harder. So it's easier to just use the Kafka approach. Like Raj said earlier, we have an import system for Whisper data. Metric Tank supports most of Graphite's processing functions built into itself, but if you send a query that it cannot fully process by itself, it will actually offload those requests to Graphite Web if it needs to. And now we're also adding support for Prometheus queries on the same data. It's basically a different processing API, but you can do it on the same data. And obviously, you can also deploy Metric Tank. This is the preferred way of deploying it as a cluster, as an eventually consistent cluster. So as far as the data goes, there's a static ring buffer. This basically keeps a certain amount of chunks in memory. The more effective way to do it is with the LRU cache, which is a secondary system that we added, which basically keeps all of your hot data, no matter if it's older or not. And then any data that's not in the static ring buffer nor in the LRU cache comes from the database. And because of this approach, for some customers, we were able to hit very high rates of requests that we can serve straight out of memory instead of having to reach out to Cassandra or upcoming BigTable. So as far as the index goes, so the index is what you use to, let's say you have a query with some kind of pattern or something like that, and you need to translate that into a list of series to then query those series. A full copy of our index is stored in Cassandra or in BigTable soon. Every instance also has a copy of the index so that it can do everything basically in memory. So all the expression parsing, the handling, searching, auto-completion, all the tagging stuff, it's all in memory. We may have to actually, as we scale out, we will probably have to address this and leave stuff out of memory, because at some point we're going to hit scalability limits that it doesn't just all fit in memory anymore. But so far, we don't have that problem yet. So a while ago, I wrote this article on our blog about various shortcomings in graphite. Even though graphite is a pretty good product that we recommend, it still has some flaws. And Metric Tank tries to address as many of that list as it can. So one cool thing about it is that you don't have to predefine your resolution of your data. You can actually, for example, start off with sending data minutely and then transition to 30 minutely or 10 secondly or every second, whatever. You can just change it as you wish, and Metric Tank will merge it together into one series. It's also better optimized for a lot of churn. For example, if you have containers spinning up and going down, same with VMs, Metric Tank handles that case of a lot of churn in your metrics better. Also, unlike graphite, we can actually roll up your data through multiple rollup functions. So by default, we roll up with sum, count, min, max, average. And we're actually working on making the selection of which rollup you want to use. We want to make that available through you at query time, as opposed to graphite, where you can by default only have one. And now we're also working on automatically detecting the interval so that you don't need, like for graphite, the storage schemas.conf anymore. It will just auto-detect everything automatically. There are two shortcomings where Metric Tank currently is a little bit worse than graphite. One is that data must be in order. We do allow a little bit of out-of-orderness, like for example, in one window of, like, say, a minute or a few minutes, we allow data to be out of order and we'll reorder it in memory. But you cannot, for example, overwrite the data of yesterday or last week or something like that. That's not supported. Also, graphite has this parameter called the X-files factor, which is used to control the rollup of sparse data. We currently don't support that, but we could add it. And so far, no one has asked for it. So I want to talk a little bit about our approach to clustering, which is basically, it's two concepts. For high availability, we use replication. And for horizontal scalability, we use partitioning. We partition our data and have different instances consuming different partitions. All right, so for the replication, you can simply run as many instances as you want. Using an orchestrator like Kubernetes makes this a lot easier. I'm having a lot of trouble pointing this exactly where it needs to be. I don't know what's wrong. Come on. Oh, anyway. Can I use a keyboard? Okay, what, with space or something? Anyway, I'll figure it out. So, as Anthony alluded to earlier, you can have a Metric Tank instance running as a primary, which means it saves data to Cassandra, or as a secondary, which means it gets all the same data, but it doesn't save it to Cassandra, and it just works for satisfying read requests. Again, using an orchestrator makes this easier to just ensure you have a certain amount of primaries running. You could also use the API to, like, manually upgrade a secondary to primary in case your primary crashed, but Kubernetes makes this easier. When a primary node comes online, it needs to know which chunks have already been saved. So to synchronize that state, you can either use Kafka or NSQ. And when instances come online and they need to serve read requests, it's important that they have a certain amount of data in memory ready to go. And backfilling all the data from Kafka makes this a lot easier. So we have in our production environment, we typically use 7 hours or more of data backfill to get that all in memory, and it makes an instance ready to go. As far as the horizontal scaling, so the shard assignment depends on your input. So with the Kafka input, which for clustering, you would, for example, set your Kafka partition, your Kafka topic to have 64 partitions or 128 or something like that. And then those are your shards in Metric Tank. So you configure your Metric Tanks to consume partitions 0 through 8 and 9 through 15 and so forth. With the other input plugins, you just specify it manually. We shard based on the metric name and the metadata so that the same metric will always go to the same shard. And the index within each instance is only for that specific shard that your instance owns to save on memory. The clusters they know about, the instances know about the other cluster members through gossip protocol. And this means that when you hit any instance, it can automatically broadcast the query to the other instances that serve the different shards and merge all the response data together and give you the response. And there's a few parameters here. So if you have multiple replicas of the same shard, then those that are most up to date with Kafka will get the higher priority. So those will be selected to satisfy read queries. And if an instance is too out of date, out of Kafka, you can configure the value for that. Then the node will be marked as not ready. And you can actually also set an option called min available shards. Some of our customers use this, for example, because the moment one shard becomes unavailable, they rather have just an error message rather than incomplete results. There's some tools that come with Metric Tank. This is, I don't know, I think this is very useful to diagnose and figure out, okay, what exactly is in the index, what exactly is in our storage, show me exactly what is coming through Kafka. There's like filtering options and everything, which makes diagnosis easy. And this is like my favorite example of this, where you can like query our index with all kinds of search parameters and construct a graphified query with custom functions, and the metrics are turned into patterns and stuff like that. And then you just pipe that into an HTTP benchmarking tool, which is a really cool way to construct a very specific workload on a specific set of metrics or processing functions. So there's some fun stuff under the hood that I wanted to mention quickly. For example, we found this bug in Go. I mean, we didn't find it. We needed help from the Go team. But there's like a bug in the garbage collector where it doesn't behave quite right, and sometimes it blocks our process for too long. So we're working with them on getting that resolved. Some other cool stuff is like we have a custom JSON decoder because the standard decoder was too slow. Context cancellation, what that does is if you have your Grafana dashboards, and it's loading a panel, but then you close your tab, or before the data comes in, if you close your browser, we will actually cancel all work in progress that was going on in the cluster to satisfy your request. We also implemented open tracing recently, which allows us to get better insights into the performance of our cluster. And we also have automated chaos testing, which basically lets us spin up a cluster using Docker Compose, then artificially introduce all kinds of network problems, and then assert that our cluster is behaving the way it should. We can also automatically trigger profiles if we know, okay, it's going to get killed with an out of memory when it reaches that amount of memory. But before it hits that, automatically trigger a heap profile so we can diagnose it later. So Metric Tank is not for everyone. But there's a few use cases where it might be useful to you. One is if you have a large-scale graphite installation. Two, if you're a Prometheus user and you're looking for a long-term storage option. If you're interested in a SaaS offering, but you don't want the vendor lock-in, as Raj explained earlier. And if you favor a known database, such as BigTable or Cassandra. So to conclude, you can give Metric Tank a try, but like I said, the experience is a little bit trickier if you just try to run Metric Tank by itself. If you run it through GrafanaCloud as a private deployment or something like that, it's going to be easier. So with that, I know that Anko from Microsoft has something he wants to say about Cosmos DB. Thanks.
Okay. Well, hello. I guess I'm one of the last between you and lunch, so I don't know if that's the best place, but I promise you I'll keep it short. I want to spend a few minutes on Azure, Microsoft, open source, Grafana. What's in it for us? And maybe It's already a surprise that a company like Microsoft is on stage when in a conference like this. But in case you missed it, open source and the whole community around that, the developer ecosystem, is getting more and more important for Microsoft as a company. Probably the thing that stands out the most here that proves that is around we as Microsoft joined the Linux Foundation, I think about 2 years ago. So for us, the world around open source, working with partners like Grafana is getting more and more important. And you see more points on the slide, like we do a lot with Kubernetes, mentioned before. We recently published something around Databricks and Spark. So there are services on Azure where we do this. In case people don't know, Azure is the Microsoft public cloud offering. So that's the name we use for that. So I have a team. So my name is Anko, by the way. I think it was on the slide. It was quite a fancy title, but in reality, I'm a software engineer leading a team of software engineers across Europe that work with partners like Grafana. And so we did the last couple of months. And the first thing we realized working together with Grafana is this thing around an Azure Monitor plugin. So you can use your tools, your Grafana dashboard, and collect all the information from Azure, like DevOps information, but also application insight information. So that's available, that's here. The next step, that's what we're working on now and expect that to come in the next few months, is also a GrafanaCloud. You've seen it before, but in this case, running on Azure. And one of the key components is something we call Azure Cosmos DB. So Azure Cosmos DB is this database that is available across the world. It's a managed service by Microsoft. So we provide the infrastructure and you basically tell us what you need. But it's not a standard relational database. There are different models. It could be a relational model. It could also be a NoSQL kind of model. It could be a graph model, document model. So different models we support in this database. And on top of that, you see again that we want to be open to the rest of the world. So we have MongoDB, but probably more interesting in the context of today, there's also a Cassandra API. So just talking about Metric Tank running on Cassandra, it could be easily ported to Cosmos DB. So when you think about GrafanaCloud on Azure, one of the APIs that could be beneficial for doing so is Cassandra. So to summarize for Microsoft, open source is getting more and more important. We really embrace it. Sometimes we provide managed services like the Kubernetes services or the Databricks services. We do the same with Grafana, so we work closely together. And for us, that is important, working with the partners in this ecosystem as well. And that might be with one of those products like Azure Cosmos DB, but there are more services that could be interesting to do so. With that, that's it.
Thanks, Elko.